In this problem, we're going to experiment with a parallel plate capacitor. The capacitance of a parallel plate capacitor is one equation that we will need. We'll also need to make use of the fact that capacitor energy is 1/2 capacitance times the square of its voltage. We'll also need to know that its charge is capacitance times voltage. Let's consider the information we have in the problem statement. We have a 1000 picofarad parallel plate capacitor with air dielectric initially charged to 1000 volts. So we can imagine the parallel plate capacitor. Its capacitance is given by the expression that includes the dielectric constant associated with air, the plate area of the capacitor, and then the distance separating the two plates, and that's the value d. To invoke this equation properly, we need to assume that the distance is substantially less than the length and the width of the plates. Now the problem statement continues by saying that the capacitor terminals are open circuited, and that tells us that no current flows out of the capacitor terminals. So any charge displacement that we have is constant. The charge can't move anywhere. We then are looking for the stored energy. Well, we know that the energy associated with a capacitor is 1/2 the capacitance times the square of its voltage. Well, we know the capacitance, and it's probably good to remember that the pico prefix is 10 to the minus 12th. So a picofarad is 10 to the minus 12th farads. The voltage, well, that's also given. That's 1000 volts, and we'll square that. The units of energy is joules. Now what happens when the plates are moved farther apart? And we'll say that the distance d is doubled. We're looking for the new voltage on the capacitor and the new stored energy. So let's think about this a bit. If the distance between the plates is increased, that means the denominator gets larger, and if nothing else changes, then the capacitance is getting smaller. Doubling the plate distance actually cuts the capacitance in half. Now the original charge that was displaced is the capacitance times the voltage. So we have the 1000 picofarads times that 1000 volts. Again, these are provided as part of the original problem statement. So that will give us some number of coulombs. Now what happens after we move the plates apart? Current is not allowed to flow because the capacitor is open circuited. That means the charge displacement on the plates remains exactly the same. Well, something has to change here, it looks like, and the thing that's actually changing is the capacitance and the voltage. We see that the voltage doubles because the capacitance is dropping. We also see then that the energy has to be going up. We say, where did the extra energy come from? Well, it actually takes mechanical force in order to separate the plates and maintain that same charge displacement. All right, let's proceed with the details. To begin with, write down the capacitor equation, which says that the capacitance at the beginning of the experiment, which I'll call C1, is given by the dielectric constant times the area divided by the spacing between the two plates, which I'll call D1. We know from the problem statement that the original capacitance is 1000 picofarads. We also know that the initial voltage, which I'll label V1, is 1000 volts. The initial stored energy then is 1/2 the capacitance times the square of the voltage. Picofarads tells us we should write 10 to the minus 12th. And we write the square of the voltage. All right, 1000 is 10 to the third. We already have 10 to the minus 12th. This would be 10 to the third times 2 for the square. That resolves to 10 to the 6th. Those combine to give us 9. Subtract 12, and that leaves us with 10 to the minus 3. Or we could write 0.5 millijoules, and we can also write that as 500 microjoules. Same thing. That was the first result we were looking for, the initial stored energy, 500 microjoules. Now we pull the plates apart to give us a new distance, d2. And d2 is twice the original distance, d1. That gives us a different capacitance and different distance. Of course, the numerator stays the same. The distance d2 is twice d1. So we write that our new capacitance is 1/2 the original capacitance. And we recall that the original capacitance was 1000 picofarads, so the capacitance now has dropped to 500 picofarads. Next, we need to find the original charge displacement. We write the original charge displacement as Q1 equals the original capacitance times the original voltage. Working through all those values, we find that the original charge displacement is 1 microcoulomb. Since we do not permit any current to flow, since the capacitor terminals are open-circuited, that tells us the current is 0, so the charge displacement has to remain the same after moving the plates apart. Now, since the charge displacement remains the same, it actually takes mechanical force to pull the plates apart. And that adds energy to the system, as we will see here in a moment. Our new voltage is V2. The new charge displacement, of course, is the same. Nothing's actually changed. So we have 1 microcoulomb, and we divide that by the new capacitance that we calculated a moment ago, which is 500 picofarads. This gives us a new voltage of 2000 volts. So we see the voltage is actually doubled compared to the original situation. Now, the fact that we've got increased voltage means that we have increased stored energy. Dropping in the specific values and carrying out that calculation leaves us with a new stored energy of 1000 microjoules. Let's summarize our problem-solving approach. First, we recalled the formula for the parallel plate capacitor and invoked the appropriate assumption. We then observed that capacitance halves when the plate distance doubles. We then calculated the initial stored energy and then compared that to the stored energy after increasing the plate distance. That wraps it up for the capacitor problem.